Okay, so hi everyone and welcome for today's session of AI Summit. For the second session, we have the honor to be with NOHA NEKAMICHE, and she is a postdoc researcher. She is a postdoc researcher specialized in computer vision, and she will host a conference called Beyond Training Data: Generalizing Across Domain.
Hello, Karim. Hello, everyone. It's pleasure to make this presentation for you and get involved with you. And yeah, so today's presentation it will be about beyond the training data, generalizing across domains. And the main idea is like how we can enhance the generalization of deep models without accessing to extra data. So let's start. As we all know that deep learning have achieved many significant success in different tasks in computer vision or even in NLP. And this is due to the availability of large data sets and access to a huge or extensive computational resources, which allow to train advanced models like vision transformers models. And the figure that I illustrate here, it shows like how transformer models overcome the ResNet models in the task of classification, but at the cost of consuming a lot of resource and and having a large models for training. So even with this, these models still suffer from a significant problem, which is overfitting to the training dataset. What does it mean? This, for example, if I have a dataset X and I train my model on it, he will learn a specific pattern that exists only on this training dataset. But what if I test it on completely unknown data? The performance will be completely degraded. And this why? This is because this data it was unseen and the model never learned about those new pattern. And this figure illustrates some result of one of the semantic segmentation models. And what we mean by semantic segmentation is that we try to attribute for each class present in the image class. Let's say we have this figure here. It have a car, road, building, etc. So the model will try to predict those classes. So when we tested on in domain, which means our training data, our training data. Let me just here. So here we have our training data. It's the in domain. The model perfectly segment and predict correctly each class as it is. Let's say this is a tree. A detected it's a tree. This is a road is the same. But when we go to hour of distribution, which means another completely data set, even though it's the same task, we can see that it's for drive-in scene and we have the same structure but a different style. So when we have a different style, we can see that common classes, let's say like car, he can detect it. But other ones, let's say this area here, normally it should be road, but he detected as a building, for example, or another class. And in other scenes, for example, when it's completely different style or little bit blur, the prediction, it becomes even worse. So here it comes the idea of domain generalization. So the idea how we can enhance the prediction on the out of distribution data sets. Straightforward solution is what we can do: collect more data and train those models on it. But collect more data requires a lot of time to first collect it and know which pattern to get, which style to cover. Should we cover just, let's say, sunny images, or images when we have winter on it all alone? And also the other thing is how we annotate them, because to train a deep learning model we need to have a grounded truth, and the grounded truth, it's the annotations of the data. So these two problems, like it's direct solution, but it's very expensive to achieve it. So this is what motivates research to look for beyond the training data set and beyond just looking for collecting data and doing things like this. So now let's understand how the domain generalization protocol works. Previously existing deep learning models, how they are trained. We have two phases. We have the training phase and the testing. And both phases are coming from the same data set. Let's say our data set it's cityscape, just for an example. So I will split my data set into two parts, part that will go for the training and part for testing. So here, when it's in the same domain, the prediction will be detected successfully, no big significant failures. Maybe we will have some, let's say, small problems, but not considerable ones. But when it comes for out of distribution, this will be reduced. And why? Because well, what we call about source domain, we mean our training data set, and the target, we mean our testing data sets that we don't have access to them during the training. So to understand why this drop happened, this is because the distribution of the data, it's completely different. We can see that here, for example, the source domain or the training data set, it have a unique data distribution, and it's completely different from the distribution of the target. And this is what we will create for us a domain shift. A domain shift, like those don't have same distribution. So for sure, the model at the end will fail to make correct predictions on the target. And in the context of driving scenes, these differences or this domain shift coming from the environment conditions. Let's say it can be locations, because, for example, images captured from African countries, it's totally different from Asian countries or European ones. Also, the weather can play a significant role. Why? Because if we take a scene in a foggy scene, we have less visibility for all the objects present in the scene. Same thing for snow or night one. So and here it comes the third factor, which is the time zone. So if the model in the source domain, it was trained only on daytime images, then it will fail when it comes for testing on night scenes or different illumination parameters. And also another important factor is the camera view, because if we capture only images from the front side, then it will be hard to make predictions if the camera it's changed in the target. And also, for sure, since our target is unknown, we cannot know what we will face in the future. So it is important, like that we try to cover as much as possible from these what we call environment conditions. So the domain generalization protocol, how they work, we train the semantic segmentation model on a source domain, and taking in consideration that we try to enhance the knowledge of this model. Enhancing the knowledge, how it can be by diversifying the source data or enhancing the architecture of the model itself. So it will have a more cover, and at the end, it will make correct predictions on the target. Yeah, so now that we understand how domain generalization problem can be modelized, we need to understand what we should learn, because here in the semantic model, we said we will enhance the knowledge, but based on what? Based that we know that we need to enhance the environment factors. What this environment factor represent in terms of data, it's the diversity or the style. So we need to understand at the beginning that in domain generalization, when we try to learn the domain invariant information, what is the domain invariant information? It can be the spatial position, which means, for example, we know all the time we have a car on the road. We never face a car on the sky. Same, for example, building, they can be at the end of the scene or next to the sky. So here we are trying to learn the context of of the domain, plus the shape and the content. So the shape, we mean, for example, we know that a person, he have this shape, a car, it has this shape, for example, and so on. And these informations are, let's say, universal or common between different domains. For example, if you train on dataset X, a person have the same shape in a second domain, similar for car and those information. What is the difference between the domains? It is the style information or the visual appearance, and this is what we call it domain specific information. And that can be represented in the style. For example, the style of the bicycle, we can find the different models. The color, maybe we can find the vegetation with less intensity or big intensity. Also the texture, for example, the road in Europe, it can be different from the road in Sahara or a different environment. So in domain generalization, what we try to force the deep learning model to learn or to focus on the common information, which we call it domain invariant ones. And we try to reduce its overfitting to the specific information. So what motivates researchers to look for is first analyzing why we get this drop when we train on a source domain or a specific data set, and when we test on a different one, it gets broken. So we here in this illustration, I try to visualize different data sets from both synthetic and realistic ones. So for the synthetic, they are collected either from simulators or gaming engines, and for the real ones, they are collected using a camera that moves through different cities all over the world. So the, how to say, the projection of these data sets, it shows that there is a clear boundary or gap between synthetic data sets and realistic ones. And this is why we have this drop, because when we train, we have access only to synthetic data sets because they are available, and we can use them and to test our protocols. So we can see that they are far from the realistic data sets, and this is what creates a drop. So the first thing, how we can enhance the diversity of these synthetic data sets, because they lack authenticity and they are not diverse enough. Because if you launch, let's say, you generated data using a simulator, there is a specific defined rules or specific styles or appearance that you can use to get to generate your data, but it's not mandatory that it will cover the real cases that exist in real worlds. So this is factor one that we should take in consideration. Second factor is the realism, because simulators, they can generate good images, but they lack realism, because we cannot how to say, for example, here we can see elimination from the reflection of the light on the road or on the sky, and which is less common or maybe cannot be completely modeled in synthetic data sets. So this is also another factor to try to how to see how we can enhance the realism using the generative models, for example. And three, the main problem that face both realistic and synthetic data sets, what we call long tail distribution. Because when we collect a data set, this imbalanced representation in the classes, it come naturally, because, for example, in the cities, we see oftenly, for example, cars, then bicycles or motorcycles. So here, this imbalanced representation, it can create the problem of overfitting, where the model will focus on learning cars more often than bicycle or motorcycle. And what we call about long tail, so the tail, it's the classes that are less common or less represented in the dataset. And and the hard, the head, it's the more frequently represented data classes in the dataset. So it can be in our case a car or building or sky, because we know like we cannot have a driving scene without a road or sky. So most of them, they are there, and the model will overfit to this ones. But when it comes for tail classes, let's say maybe pedestrian or train, because we don't see a lot of train in the cities, so the model will fail on predicting those informations because of this imbalanced representation. Yeah, so how, state of art, now that we understand the domain generalization problem and the problem of overfitting, and how to say the different characteristics of existing data sets, we move to see how researchers involve or try to enhance the domain generalization. There is three ways to do this. It's either on the input space, and the input space, we mean by this augmenting the source domain dataset without accessing to the target, because so far the target is unknown, we do not know it. But in research we need to validate our approach, so there is a common existing target datasets that we test on them, but we do not have access. So the idea is, we try to augment or diversify the style of the input data. The second one, it's on the feature space. It's either by diversifying the features extracted from the encoder, or regularizing the features, which means, for example, like I have my encoder, I add another encoder in which I try to extract only features that are common, or remove the style on at the feature level. And the last one, it's on the output space. The output space, which means we try to correct the final predictions, or enhance the prediction at the end. And since this problem is very hard to achieve, because even for humans, for example, if you learn to speak English and French, sorry, and you get involved in a new language, let's say Spanish or Italian, and it's similar a little bit to French or English, but you cannot understand fully because you don't have previous knowledge. So how you expect from a deep model to achieve this? So this is why some works, they try to combine even both. For example, their contribution, it will be on the input and the feature, and sometimes even the three at the same time, because it's really hard like to cover all the cases without knowing on what you will test. So, and this is what makes domain generalization even harder, because there is a similar domain to this one, which is domain adaptation, in which you know your target and you try to adapt your model to it. What does it mean, you know your target? You can access, you can use a small subset of your target by augmenting the source or injecting the style of the target during the training. But in domain generalization, we don't have this option. This is what it make it even more harder, like to accomplish. And yeah, so globally, like we have three aspects to play on it to enhance the generalization, and most of works, they as I mentioned, they contribute to two or three aspects at the same time. So let's start with the first space. The first space, their idea is like how I can enhance the style of the source. So the idea is like to use images that look like target. It can be collected from internet, or from other existing data sets, like, but not your actual testing data sets. So the idea, it's what, to use style transfer models. It can be here, for example, VGG, encoder decoder, and using the layers of ada-in, because ada-in, it allow us to inject the style. So the encoder will start first by extracting the features, and the features from, we consider the source image as a content, and the content means like this is the structure, or this is like the original information, and I want to inject a style from another image. And this encoder will achieve this, so we'll extract two different informations: the original feature from the source, and style information from image that we consider it look like as a pseudo target, and then using ada-in layer to inject this one. And the idea here, it's like just like to shift the features using the mean and standard deviation, and then inject and then decode it back using a decoder to get a stylized image. And in this way, we create a new augmented version of the source. And then we train the model, the semantic segmentation model, using both images. And we know that the source, it's already, we have its labels. So for the stylized image, it will have the same label, but a different style. So by augmenting the style, the model what will try to learn different styles. So he will try to cover as much as possible from the appearance styles. So when we test on the target, it can achieve a good performance. But these ones are limited in terms of diversification, because they just enhance the style information, no scene augmentation. What I mean by scene augmentation, for example, I cannot generate a new car here, or for example, I know the unbalanced classes, which are bicycle or motorcycle. I cannot generate a new one here, for example, to enhance the prediction on this one. Another interesting works, like they propose to use GAN models. And since we need like to maintain the structure of the source image, so they propose, most of them, they propose to use a cycle GAN. So the idea is like to have a source and pseudo target image, and the first generator will generate a fake target image, and the second generator will reconstruct the original source image. This is for the training part of GAN, and the same way in the other direction. And at the end, the semantic model will learn using the original source image and the fake target one. And also this one, it modifies only the appearance information. Another works, they propose to use Fourier transformation, which is less, how to say, it use less computations, because it's not trainable way. It's just a mathematical formulation that you apply it on the image. So according to them, they try to analyze the spectrum, because when we use Fourier transformation, we will have like a frequency representation of the image. So they analyze this frequency and to split it into two categories: DIF, that represents domain invariant information, and DVF, that represent the domain variant one. So the idea is like to randomize this part, because the domain variant, it means it's the style of the original image. So what they do, they bring images from a real data set, which is not existing in the target. So the target, forget about it, we do not have access to it. So for them, for example, they can take it from ImageNet or other available data sets. They also apply the same transformation to decompose this and modify the style of the source using the variation information or the style information of the other image to get new randomized one. So they augment the source, and then also here they use both to train the semantic model. Another recent works, and also like actually, if you go and you are out of curiosity, most of techniques or recent works, they are all diffusion based works, because like the evolution of, or the interests for domain generalization gets like at the same time with the evolution of diffusion models. So most of them, they switch from GAN or style transferred models to diffusion models, because they allow a better generation, high quality images, and also they afford the possibility to control and guide the generation. For example, in this figure here, I chose it randomly, so we can control the generation using the semantic models, and we know that in the source we have the semantic models. So using the fusion model, we can use, for example, a variant that calls ControlNet, that allows to inject semantic map or depth estimation map or any other condition to guide the generation and generate completely new scene, and then use this alongside with the original images to train the model. Also, another interesting way, especially with the rise of LLM agent at the same time with the fusion, some works they think why we do not augment the scene structure, as I mentioned before, because we know the main important also problem comes from the less representation for some classes. So what they do, they propose to generate new scenes using LLMs. For example, I will give instructions. I know in my source dataset, I have less images that have bicycle, motorcycles, let's say pedestrian. So I will ask an LLM to generate for me a scene that have more bicycles or buses or trains, etc. And then I get completely new scene. But here the real, how to say, the real problem with this ones, that we generate only images, we do not have annotations. But this is not real problem, because like in state of art there is other technique or learning strategies that allow to use images without labels and generate pseudo labels for these ones. So mainly works that propose to augment scene representation, they involve another let's say aspect, not just generating in the input space, but also combined with the feature space or output space, in which we will see now um, how they work by proposing different learning strategies, etc. So now we finish from the input. So just a small summary for the input space. It's I have my source domain, and what I do, I try to augment the representation, either only style or control or generating completely new scenes from just with the text, or even like using semantic maps. Once this is and but this is not completely enough, because like we try to cover as much as we can styles, but if the model is still like overfitting to this data, we cannot like cover everything. This is why it is important also like to go one step further and look inside the semantic model to see what we can enhance at this level also. So here, like, works what they try to play with, they try to play at the let's say the heart or the encoder of the semantic model, to see how they can enrich or either diversify or regularize the features of the model. And this works, for example, what they do, they, as we said, like they can perform initial augmentation. It can be one of the previous techniques, or just like simple augmentation, like we know, like color jitting, or just increasing contrast or reducing contrast. And moving one step forward to apply randomization on the feature level. For example, here, because we have two levels, two different image augmentations, so in the feature level we will have different statistics. So the idea is to use ada in layers at the feature level to inject the style of the first image on the second, and the second on the first, and then make another consistency loss to align, let's say, their predictions. So in this case, we learn the model to how to say, to focus more on the content or the invariant information and not on the style, because I randomize the second image with the first one, with the style of the first one, and same thing for the first image. And then I force the model to make the same predictions at the end. So when we force the model, which means we are trying to say whenever the style make the same prediction on these figures or these scenes. And by doing this, the model will learn how to say discriminative features. So whenever you give it a style, it will extract only the content information or the information that is common, which is shape, object, etc. So the score will be better, or the prediction will be better when we test on the target. Another way to do this also, it's the contrastive learning. But before explaining how it's gonna be, we need to understand contrastive works, how they work. The first, for them, they make two different augmentations. So the model will have like first augmentations and second ones. Let's say the first one, we can consider them as a positive augmentation. What does it mean, positive? Let's say I have image for a dog, and I try to play with the color, the rotation, etc. So I create a new views for this dog. So the idea, what I do in the loss, I try to force the model to make the same predictions on these ones. So what I do, I try to minimize the error of the prediction on these two images. On the other side, the negative examples or the views for another class, let's say it's a chair here. So I have two augmentations, and I consider them as a negative for the first class that I have. So the idea is like to maximize the distance between them. So I try to repeal or make as much as I can the prediction look far from the predictions of the first one. So contrastive learning is like I have two different augmentations, positive and negative, and I try to minimize the error or the distance from the input and the positive examples, and maximize the distance for the negative ones. So in our case, because we know, for example, we can have images for bicycle and motorcycles, and those two classes for the model, it's a bit hard and they can confuse between them. So what we can do, we can augment the image for the bicycle and force the model to focus on making a correct prediction on the bicycle, while the augmentations of the motorcycle, I try to reduce or maximize the distance and reduce the correlation between them. So this is a way how we can do, but always we can see that like the input space techniques, they are always here, because we all need like augmentation or a different representation of the input, so I can use this learning strategy. Another way to also handle domain generalization is to use meta learning. And the meta learning, it's we can consider it as a B-level optimization. Why? Because in this specific training way, we have two losses. We call it inner loop. So it will be the first update that we will have, and then an outer loop that it will be considered as the second. So the first or the inner one, we consider it as the model is trying to understand or make good prediction on the source domain, or on learning both how to say variant and invariant information. And in the outer, the model is trying to make a fast adaptation, and we can consider it as a meta test, because it's the second step that the model will try to correct itself, because in the first one we have the source domain that we are using. So for sure the model can overfit at this first step, but to reduce this overfitting, it comes the second update on the meta test. And here, this is the main challenge, because if we use the same data set, for example, I have GTA, for example, I split it into, let's say, 100 images here in the training, 10 for the meta test. The model will overfit, and this way of working, it cannot work. So the how to say, the main work, or the main important thing in meta learning or meta training, is that the meta test should be completely different from the meta train. And what I mean by this, it means like in terms of distribution, they should have different distributions, which means not just taking one data set, I split it and done. No, here in the meta test, we can use the augmented data that we see in the input space. So I can like generate new scenes or use guns or whatever, just like to have a new augmented data. So when I make the second update, the model will try to avoid overfitting and learn only the discriminative features. So in this framework, we always have two updates. The inner, we can use the source data. In the second step, it will be complete. It should be another completely data set. And then there is another way to do this, because the other one in meta learning, it's like we need labels for meta test, because it's fully supervised learning. As we can see, for the loss, we need to have labels, but which make it more constrained, because in domain generalization, we cannot have access to the target. So even no images and no labels. So if I generate completely new images, then I will face the problem how to prepare the labels for it. So we can, here we are restricted only how to say to the existing source domain. I use only style transferred to augmented, or find a different way that we will see it at the end of this presentation. And then here it comes the other way of why we do not use student-teacher approach. And in student-teacher approach, the model tries to correct itself or correct its predictions by using Emma update. And how it happens, so you will have your source images, you make the first prediction, and then you update the weight of the teacher. So you are kind of making just a copy of the student. And then this teacher, what we will try to do, use a new generated images that we have, for example, and create pseudo labels for them. So these pseudo labels will be the ground truth for the student. Then we will have another update for the student using these pseudo labels. But for sure, this teacher at the beginning is weak, because he cannot make good predictions on completely new images. But with the time, it gets refined more and enhanced more. And we can say it like, we can see it as our learning, when we learn a new thing, and learning by doing. For example, if I want to get involved in a topic, I try to learn it alone, but I, for sure, at the beginning, I will make some mistakes, but with the time and with enhancing my knowledge, I will get more and more better. And it's we can see it like this. And this architecture, it allows like also to reduce the reliance on labeled data, which make it more efficient than the previous ones. Now let's move to the output, because we talked so far, we see the input, we augment only the scenes. The second one, we enhance the learning or the feature extraction of the heart of the model. And now we can arrive or to the output space. The output space, what does it mean? We try to refine the predictions of the model. In adversarial learning, we know like adversarial learning, we have always a discriminator that tries to make it, let's say, false and true. So the idea is like, let's say true, which means it's for the source, and false, it's for the target, for example, or vice versa. So the idea is like to connect also a discriminator in parallel with the classifier, because the classifier, it is the part that will allow us to get the final prediction. And the discriminator will try to criticize the feature extractor of the model. So it will tell us if the prediction it look like the source or it look like a target. And since we know that we do not have the target, but we know that if it looks like something else than the source, it means like the feature extractor succeed to extract only a common information and not overfit into the source. So the idea is like to maximize the prediction to look far away from the source of the discriminator. By doing this, we will reduce how to say like the overfitting to the source domain, because like if the feature extractor even on this is, let's say this is the source image and I made another augmented image and I feed it and I find it's look like the source, this means like the model is like overfitting. So I have to change something either in my feature extractor or my input data, or find another learning strategy to use. So the idea is like to reduce overfitting to the source by using adversarial learning. And finally, another one, because like we saw before, like in contrastive learning, we had we try to minimize the difference between the positive and the input data and maximize the distance to the negative ones. There is another way to achieve this. It is like we try to refine only the predictions using a consistency loss. So the consistency learning way, it allow us like to make different from a different augmentation similar predictions. So the idea is like the consistency loss, it will just work on the classifier. So we will learn or force the classifier to make exactly same prediction even we have a different styles on the input image. Let's say this is the source, this is what I generate or augment using different technique. So I try to minimize the differences in the prediction at this level. So basically, like this is like how researchers deal with domain generalization. And to finish, I wanted like to share some of my contributions that I made during my PhD. So the first one, we looked on what exists in state of art, and then we try to build our approach inside the meta learning at the beginning. So here we face two problems. Meta learning requires labeled data. This is one. Second, requires diverse data that is different from the source. But also, like if we use the labels of the source domain, which means we still in the source domain in terms of like geometric shapes and things. So here it comes the idea why we do not start generating a synthetic images from labels and not from images. And then introducing this new generated labeled data in a meta learning framework. So what we did, basically we started by first training low rank representation of diffusion models to generate completely new masks. And for this I used existing masks and I guide it with the prompt. So the prompt, it will contain only the classes that are represented here. But we know like diffusion models, once you train it on something, you can in the inference mode, you will just present the prompt and they will generate completely new. It can be completely different from what I mean, in terms of shapes or classes that you want, not in terms of data. But since they are labels, so the generation, it will be completely like this. So I will generate new labels and then convert them to label IDs, because this is a colors and it's hard to train a model on it. So it's better like to map these colors to just IDs. Let's say 0 for grace, 1 for sidewalk, etc. So this is just to understand how it happened during the semantic model, and then use a model that will translate this RGB mask to label IDs that contain only the ID of every presented class. Then use this one, this RGB mask, to generate new scene. So this new scene, I will have like the label and the label and the scene. So now I can use it as a meta test in the meta learning framework, and the meta training, it will be the source domain that we have. So why it's interesting to generate first labels? Because we can play around these factors. I mean, we know, like, if we have less images in the source of bicycles, I can just with a prompt generate new bicycles and so on. So this is some examples of label generation scenes. And here, just like the distribution of classes, we can see that my data set, the GTIA, it's the source. This my data set that I create, we can see like we enhance it for bicycle and for some other classes, for example traffic sign and so on. And here just some examples how we diversify the scene generation, because we start by generating a semantic map, and then diversifying the scene by diversifying, for example, location, then weather, then daytime, etc. And this is some how to say scores or results on each class. We can see like this is confirming the second row. It's using meta learning, but using only GTIA, which means meta train, meta test, both are in using GTIA. We can see that like the scores, they are not enhancing that much, and even sometimes it's worse, as we can see here. Why? Because the model is overfitting, and meta learning, it needs new diverse data in meta test to give you like the improvement. So then when I introduce my data set, I can see like some significant improvements, especially for the less presented classes. Then in the second contribution, so now I'm moving to the second contribution. We used like the framework, the original framework, it was the student teacher, because like in my first contribution, we were restricted to labels. So we generate first labels and then the scenes. And like generative models, sometimes they are not very accurate. So you need to clean or remove the misgenerated ones and so on. So now we moved to use a student teacher network that allow to introduce pseudo images without labels. So the student will first be trained on the source dataset as it is. Then in the meta test, and then the second step, that the teacher will try to prepare the pseudo labels for the generated scenes using another model called Flux, and then using these pseudo labels to make the second prediction by the student. But this is not enough, as we know in research, as a contribution. And also we know that the problem of overfitting always coming from the feature extracted of the encoder. And the encoder, if it's overfit, even when you introduce new data, you cannot solve the problem just by generating the data. So the idea, it was to use orthogonal features and reduce the correlation between the extracted features for each class. So here, how we solve this problem. We know that we have the label mask for the source, and I have the classes. So what I took, I used another clip encoder. It's just a text encoder. I feed it with the classes, and then I applied SVD decomposition to create unique vectors. So those vectors, let's say the vector that represent road is completely different from the vector that represent car, etc. And then reconstruct the orthogonal embedding using the feature map. So here, once I reach the level of orthogonal embeddings, what I do, I make a loss that compares the visual features from the feature extractor and compare it with this orthogonal embedding to reduce the overfitting between the classes. Here's some visual result, like, because like the deep inside is sometimes hard to be understood. It's better to have some visual result. So let's say this is my source image, and this is the label. In the label, I know what classes are represented, so I encode that class representation with a text encoder. And then what I do, I apply the SVD decomposition to get orthogonal features, and then I try to map the orthogonal features. So here you can see this is the heat map representation of my orthogonal features coming from the label, and this is the heat map of the visual features. So after different iteration training, we can see they are almost similar. I mean, similar for sure. They will not have the same intensity because they are the how to say, the values can be different, but we can see that the model learns to unify. Let's say we know this part, this region, it's for road, so the feature extracted for road, they get a unique value. So this is a reduced confusion with other classes. Let's say also for bicycle, it have a different heat map. This means like it know now like how to differentiate between bicycle and motorcycle or things like this. And here like different how to say, visualization of different feature layers of the encoder, because just to here to check if this orthogonal constraint from the orthogonal features, it's still respected all over the layers or only on the first. We can see like it's still like knowing that this region, it will be for bicycle, not for something else, or confusing it with another thing. And here's some predictions. This is like this is the ground truth created by the teacher. We can see that the teacher succeed to make a good prediction on the pseudo target image. This is what I generate using Flix, and the teacher with the time learns how to predict correctly that this is a sidewalk, this is a road, this is a bus, etc. And especially with this orthogonal constraint, the decision boundary of the teacher gets really better in terms of predicting the exact, how to say, pixels for each class. And here some visual results. We can see that when we analyze the results, we focus mainly on the less presented class. Let's say wall, for example, it gets from 49 to 51, pole also from 43 to 50, and so on. So we can see that we get a good improvement in the less represented classes. And of course, sometimes we get some drops, but we can tolerate these drops, especially for the common classes, because we know like in the target, like the model will not like forget of predicting a car, for example, or sky, because they are already common. But if the score is not good for bicycle, then this is the problem. Yeah, so basically this is like how we try to deal with the how to say, domain generalization. And also like we can see like the score is not like reaching I don't know, 80% or 90% for all the classes, because the challenge is really hard, because you don't know your target. So if we get an improvement of 1 or 2%, that this is good, because you are focusing on completely unseen data. Yeah, so this is it. Thank you for your attention. And yeah, if you have any questions, you are welcome to ask them. We can start with the session of questions.
Okay.
Okay.
So thank you so much for the presentation. It was so interesting from beginning to the end. I personally have a question.
Yes.
Like when you use cycle GANs and style transfer for modifying the input space, I
Mm-hmm.
think that it could be really computational. It could be, yes, it could cost computationally a lot. So, do you personally think that we should more focus on feature space rather than input space for real world application?
Actually, based on my experience, like if you augment on the feature space, how to say, it's not visible for us to see really, even though we have heat maps, we can visualize the statistics, etc. But we have no guarantee, like to how to say, like to see like exactly if I make the, for example here, yeah, this one, yeah, this is a good one. Yeah, if I make the randomization or augment on the feature level, it is 100% I am 100% sure that it's well augmented, because we know, like we are trying to play with the mean and standard deviation to enhance the distribution of the other image. But sometimes this is not enough, because you shift a little bit the data, but you are not really enhancing it a lot. And according to what I saw in the state of art, all the feature based approach, they are getting lower score than the other technique. Yeah, so for sure, let's say, for example, GAN or other technique, they are computationally um, uh, a lot. But if you get a better result with them, then we can tolerate it sometimes. So basically, according to my knowledge, like on the feature level, it gives a good result. But recently they are not anymore using them, because let's say they are saturated. Because in other feature level, what you can do, you can just like shift the statistics using mean and standard deviation. But this is not enough, like to cover everything. I don't know if my answer is a little bit clear, or
Yeah, I
um,
see. I understood. Thank you. We
you're
have a
welcome.
question in the chat. To
Yes.
what extent are domain generalization techniques utilized in fields beyond supervised learning, such as reinforcement learning and vision language models?
Can you please repeat the question, or maybe I can show
Uh,
it here?
the- there's no problem. To what extent are domain generalization techniques utilized in fields beyond supervised learning, such as RL and VLMs?
Yes, actually, like now, what real recent ones, they start using vision language models, or what we call it foundational models. Why? Because first of all, they are already trained on large models, and also they get benefit from both, how to say, language and image information. So when you bring those both informations, like you get more enhancement. And as I present in the second contribution, when we introduce text as a feature regularization plus the orthogonality, it gives really a good performance. We reach 64 as a score. I know it's still generalization, but it's also a good score compared to the previous technique, using 50, getting 52 or something like this. Yeah, I mean, vision language models are good, and are, they can get really better results. But also, like they still, like you need, you to still have a, a lot of computational powers to use them. But yeah, like I mean, like according to my knowledge and what I saw now recently, all the research, they are converging to VLMs to use them. Because like let's say, the problem of unbalanced classes, they can guide it with the text prompts during the learning. So if you guide it with this, so you are reducing the confusion between classes, and boom, you enhance the score. So yeah, it can be extended for using these ones.
And what about small language models, like as an alternative?
Like what?
Small language models.
Uh-huh.
like SLM, as an alternative if it's too computationally cost.
Um, it depends because if they don't cover all the cases, because also like you have when you pick um, small models, you need to see on which data they were trained, to see if it match your let's say your task or no. And maybe they are not trained on already, I mean, pre-trained on a large information, so when you will use them um, to regularize your features, it will not work, because they will not bring, how to say, enough diversity, or allow you to get better performance. But at the same time, they you may can get some surprises and get a better score, because this is the of like this is like the main challenge in the main generalization. You cannot know what surprise you will get until you test and you see at the end, because you don't have access to the target. So maybe if you use this small language model and you know how to guide it well, or you design well your architecture, you can get good results, um, or let's say results that are acceptable or similar to the large ones. So it is okay, because sometimes we can tolerate some drops compared to large models. Mhm.
Okay, thank you. I
You-
also have one last question.
yes.
Is like when I saw your first PhD contribution,
Uh-huh.
uh, do you often target the tail class, and is it always better to target this specific class for the domain generalization?
What you said, the classes for the classes.
No, like when you use domain generalization technique, do you always target the tail class? And is it always better to target this specific class? And how do you do it?
Yes, 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 for sure. Because like for the tail classes, you have less representation. If you the main idea, you take your source domain, you try to make a plot to see how your classes are. The frequency of classes, I mean, how many images a car appears on it, how many images you have a bicycle. If you find like you have only, let's say, 20 image of I don't know, 1000 image or 10,000 images, it's for bicycle, so the model will not learn it. And also like, because when we train a deep learning model, the data loader, it's picking randomly. And let's say if you have 1000 image of car and 20, so how the probability that you will pick this bicycle at the beginning or during the training, it will be really less frequency for these ones, so the model maybe completely will miss learning them. So this is why it is important. I mean, like, for me, at the beginning, we this is what we face. We did not know that this is the main problem, this is the major problem, because at the beginning I was just generating new data, augmenting and testing, and sometimes you get to like surprise, it's not enhancing at all the results. And but once we know that the main problem it's the tail classes, everything changes. Like, if you target the tail classes, you will get always a good performance. It is clear, because like the I don't know, like if you can see here from some results, you see here, this is baseline, and this is only using GTA, which means like here we don't have any, let's say, new class or something, or improvements for the classes. You can see, for example, sidewalk, there is only 2%, and 2% it's coming from the meta learning, not from your data. So like maybe like if you repeat it twice, at the second time get a little bit more sidewalk. For example, for traffic sign, because it's less, maybe in the second round of update it did miss it completely, so it gets a drop. But when you target these classes in your generation, then it gets better. You see, like it's completely
Mm.
huge difference. Like when you generate the underrepresented classes, it's game changing.
Okay.
Mm-hmm.
Uh, I think that's it. It was really interesting. Thank you so much for your time once again. Thank you so much for this conference, for sharing your expertise with us. Ah, we have also another question. Uh,
Mm-hmm.
are SSL techniques used?
In my No, for me, I didn't use them, and I don't think so. In the context of driving scenes, I didn't saw a work that use this technique, but maybe in another context or another field, because domain generalization, it's a concept. It can be applied for classification or any other problem, like because it's all the protocol, it's clear, like you have training and test, and you don't have just access to the test, and you can introduce whatever you want. According to my knowledge, no, but vision language models recently, yes, they start introducing them, adding some improvement on the baseline or introducing new constraint on the feature extraction to get better results. Yeah, this is what
Like,
I know.
what?
In the context of driving scenes.
Okay, like, what do you mean by SSL techniques? I never heard about them.
SSL, like it's the small language models, no?
Ah, it's self-supervised learning.
Sorry. SSLs. Yeah. Okay. I thought you said the small language models because we discussed it before. Sorry.
SLMs.
Like
Okay,
just
yes.
a small update for this. Self-supervised. Yeah. Self-supervised ones, because like I showed you like the pseudo labeling. It's it's one of the technique of self-supervised learning. In self-supervised learning, you have like you can achieve it either by contrastive learning or by pseudo labeling, and in pseudo labeling the last version, it's the student teacher model. So in our second contribution, yes, we use it, but according to my knowledge, it's not used in domain generalization before, but only in domain adaptation, because domain adaptation, it's similar to domain generalization, with the main condition. For them, they have access to the targets. For us, we don't have access to the target. But also, like with the, how to say, with the rise of diffusion models, and that we can generate completely new scenes just from typing the text, we could use the framework of domain adaptation and extend it to domain generalization. Like, how to say, we can call it like unsupervised domain generalization subcategory. Voila.
Okay, I think
Okay.
it's
Hey,
pretty
I'm
clear.
sorry, because I thought you said the small language models, not self-supervised learning.
There is no problem. I think that we don't have any more questions. So thank you so much, Noha, for your talk once again. It was a pleasure having you with us, and thank you. Thanks for everyone who attended the session. And yes, we'll see you next time. I hope it will not be
Okay,
the
it's
last
my
time.
pleasure. And keep doing those amazing events. It's really a pleasure to be a part of it. And I hope the presentation helped you to get involved in, let's say, new topic, or get some knowledge, or get a plus on something else that is different from what you are doing in your daily activities. And yeah, good
Mm.
luck with the rest of the talks and the sessions. And have a nice
Thank you.
day. Thank
You
you.
too. Thanks. Good night.
Thank